Unexpected experimental results challenged this classical picture. At the atomic and subatomic scales, nature behaved in ways that could not be reconciled with Newtonian determinism. Max Planck introduced the revolutionary idea that energy is quantized, not continuous. Niels Bohr argued that electrons do not orbit the nucleus like planets, but exist in discrete energy levels described by probability patterns. Erwin Schrödinger developed wave mechanics, showing that particles are best represented not as points, but as probability waves. The most radical insight, however, came from Werner Heisenberg's uncertainty principle. He demonstrated that it is fundamentally impossible to know both the exact position and exact momentum of a particle at the same time. This is not merely a technological limitation, it is a structural feature of reality itself. Quantum mechanics therefore asserts that nature is predictable only in terms of probabilities. One can calculate the likelihood of an event, but not the event itself with perfect certainty. The universe, at its deepest level, is an interplay of possibilities. Number 3, two visions of predictability. The contrast between classical and quantum mechanics is not simply a technical dispute. It reflects two distinct visions of the universe. Classical mechanics. Nature is exact, calculable, and determined. The future unfolds from the past with mathematical necessity. Quantum mechanics. Nature is open, probabilistic, and intrinsically uncertain. The future contains many possible paths that collapse into reality only upon observation. These perspectives reshape how we interpret the world. The classical view offers stability and control. The quantum view introduces humility and creativity. Yet neither is wholly sufficient alone. Modern physics uses both frameworks: classical mechanics for large-scale systems, and quantum mechanics for the microscopic world. Together, they reveal a universe that is neither rigidly predetermined nor chaotically random, but one in which order and openness coexist. Number 4. Conclusion. The debate over predictability in nature shows that our understanding of the world evolves as our tools and theories deepen. Classical mechanics gave us confidence in natural order, while quantum mechanics taught us that uncertainty is woven into the fabric of reality. Both perspectives remind us that nature is richer than our expectations. Whether described through precise laws or probability waves, the universe remains a place of structure and mystery, inviting continued exploration. Is a continuous, polished English essay with a natural academic flow. It has subheadings, but the prose is unified and narrative-driven, just as an essay should be. Two visions of gravity: Newton, Einstein, and the shape of the universe. Introduction. Every human being has felt gravity long before learning its name. It presses our footsteps into the ground, pulls a falling apple toward the earth, and guides the moon across the night sky. Yet, the meaning of this familiar force has been explained in two remarkably different ways by two of history's greatest thinkers, Isaac Newton and Albert Einstein. Newton described gravity as an invisible attraction acting between masses, a picture that works perfectly in the world we live in. Einstein, however, reimagined gravity not as a force, but as the curvature of space-time itself, a description that becomes essential once we step beyond Earth and enter the vast architecture of the cosmos. This essay explores these two visions and shows why each remains indispensable in its own domain. Newton's gravity, a universal pull that orders the Earth. Newton's 1687 theory of gravity was breathtaking in its simplicity. He proposed that every mass in the universe pulls on every other mass with a force proportional to their masses and inversely proportional to the square of their distance. Without explaining how the pull occurred, Newton succeeded in explaining what happened: the fall of objects, the tides of the oceans, and the harmonious orbits of planets. This picture works beautifully on Earth. Everyday speeds are slow, distances are modest, and gravitational fields are gentle. Engineers launching satellites, architects designing bridges, and physicists calculating projectile motion all rely on Newton's equations. Within the boundaries of daily experience, Newton's gravity is accurate, intuitive, and powerful. It gives us a world that is orderly, predictable, and stable. Einstein's relativity, a universe shaped by curved spacetime. 2 centuries later, Einstein saw beyond Newton's picture. He realized that the idea of a force acting at a distance was incomplete. His 1915 theory of general relativity proposed a radical alternative. Mass and energy curve spacetime, and objects move by following these curves. Gravity is not a pull, it is a path. Einstein's vision explains phenomena that Newton could not touch. The unusual orbit of Mercury, the bending of starlight near the sun, the slowing of time near massive objects, and the existence of black holes all flow naturally from the curvature of spacetime. Modern discoveries, such as gravitational waves, first detected in 2015, continue to confirm Einstein's insight. This geometric understanding becomes essential on cosmic scales. The universe contains extreme environments with enormous masses, immense distances, and velocities approaching the speed of light. In those regions, Newton's calm and predictable world dissolves. Einstein's equations, however, remain steady. They describe the core of stars, the edge of galaxies, and the expansion of the universe itself. Why Newton works on Earth and Einstein works in the universe. The difference between these two theories is not a clash of correctness, but a difference in scale. Newton's theory is not wrong. It is an approximation of Einstein's deeper truth. Where gravity is weak and speeds are slow, Newton's equations emerge naturally from Einstein's. In this sense, Newton is a faithful portrait of the world near us, while Einstein is the larger map of the world beyond. On Earth, the curvature of spacetime is so gentle that we do not notice it. Objects move almost exactly as if gravity were a simple force pulling them toward each other. But in the universe, where mass bends spacetime like a heavy stone warping a stretched sheet, Einstein's geometry becomes the only language that fits the landscape. Thus, one might say, Newton explains the neighborhood, Einstein explains the cosmos. Conclusion: gravity, the most familiar force of all, turns out to be one of the most profound. Newton revealed its mathematical order in the world around us, and Einstein uncovered its deeper structure in the universe at large. Their insights do not compete, but complement each other. Newton gives us the physics of bridges, rockets, and daily motion. Einstein gives us the physics of galaxies, black holes, and the unfolding universe. Together, they represent the human effort to understand creation, from the ground beneath our feet to the farthest stars. Below is an English essay written in a scholarly but accessible style, structured with clear subheadings. The tone is professional, and the flow is designed for lecture, academic presentation, or publication use. The 1927 Solvay Conference, Bohr, Einstein, and the Shape of Quantum Reality. 1. Introduction. The Fifth Solvay Conference, held in Brussels in 1927, marked one of the most dramatic turning points in modern science. 29 of the world's leading physicists gathered, 17 of whom were Nobel laureates. At the center of the debate stood two towering figures, Niels Bohr and Albert Einstein. Their disagreement was not merely about equations, but about the very nature of reality itself. This essay examines Bohr's Copenhagen interpretation, Einstein's realist objections, and the continuing significance of their debate. 2. Bohr's Copenhagen interpretation. Bohr's view of the quantum world can be summarized as a radical shift in how nature must be understood. He argued that quantum phenomena cannot be described independently of the measuring process. 2.1 Probability as the language of nature. In classical physics, physical quantities such as position and momentum were thought to exist with definite values, whether or not they were observed. Bohr overturned this assumption. The wave function, he said, describes probabilities, not hidden certainties. Quantum theory therefore demands a probabilistic language, not because of ignorance, but because nature itself reveals only possibilities until a measurement occurs. 2.2 Measurement and wave function collapse. For Bohr, measurement is not passive observation. It is an interaction that brings about a definite outcome. The wave function collapses into one value at the moment of measurement, and before that point, it is meaningless to speak of the system having a definite state. 2.3 Complementarity. Bohr introduced the principle of complementarity. Certain properties, such as wave behavior and particle behavior, are mutually exclusive yet jointly necessary for a full description of a quantum system. Reality, in this view, does not reveal one fixed character but presents different faces depending on how we choose to observe it. 3. Einstein's realist and deterministic objections. Einstein respected quantum mechanics as a successful mathematical theory, but he firmly rejected Bohr's philosophical implications. His concerns were grounded in the belief that nature is fundamentally ordered, coherent, and independent of human observation. 3.1. God does not play dice. Einstein believed that probabilities result from incomplete knowledge. In his view, electrons must have definite positions and momenta prior to measurement. A theory that cannot describe this underlying reality is, in his judgment, incomplete, no matter how successful its predictions may be. 3.2. The demand for physical realism. For Einstein, physics must describe what is truly there, not merely the outcomes of experiments. He insisted that a scientific theory should give an account of the world that exists independently of observation. His critique foresaw deeper puzzles in quantum theory. In time, this led to the EPR paradox, 1935, where he argued that quantum mechanics implied spooky action at a distance, which he considered unacceptable for any complete physical theory. 3.3. The search for a deeper theory. Einstein hoped for a more comprehensive framework beneath quantum mechanics, one that would restore causality and realism. Although he did not live to see it resolved, his challenge pushed later generations to investigate the philosophical foundations of quantum theory more seriously. 4. Evaluation of the debate. The Bohr-Einstein debate remains one of the most influential intellectual exchanges of the 20th century. It shaped both the development of quantum theory and the philosophical discussion about scientific truth. 4.1 Experimental success favors Bohr quantum mechanics, interpreted through the Copenhagen lens, has been extraordinarily accurate. It underlies technologies such as semiconductors, lasers, nuclear magnetic resonance, and quantum chemistry. Experimental tests of Bell's inequalities in the 1960s and 1980s further undermined Einstein's local realism, confirming that quantum systems display correlations that cannot be explained by classical, deterministic models. Broader 4.2 philosophical depth resides with Einstein. Yet Einstein's objections have not faded. Questions about the nature of measurement, the meaning of the wave function, and the reality of unobserved states remain unresolved. The rise of alternative interpretations, such as the many worlds interpretation, Bohmian mechanics, and cubism, shows that modern physicists still wrestle with the questions Einstein raised. Einstein lost the empirical battle, but his philosophical challenge continues to shape the landscape. Hammer 5. Conclusion. The 1927 Solvay Conference did not produce a final answer, but revealed the tension at the heart of quantum reality. Bohr argued that nature is fundamentally probabilistic and reveals itself only through measurement. Einstein countered that the universe must possess a deeper order, independent of observation. Today's physics endorses Bohr's framework for its predictive power, while Einstein's questions remain vital for understanding what the theory ultimately means. The debate continues to inspire physicists, philosophers, and theologians who seek to grasp the structure of reality and the mysterious balance between certainty and possibility. Q1. In what ways does Bohr's